In this section, we will discuss the standard normal probability distribution. In the last section, we learned that if we look at normal probabilities through the eyes of their corresponding z-score intervals, we can use a single table to compute all probabilities. We also learned that for a continuous random variable, the area under the curve of an interval is the probability of falling in that interval. In this section, we will focus on learning how to compute probabilities under the normal distribution curve for any z-score interval. If X is normally distributed with a mean of mu and standard deviation sigma, then the z-score formula here on this slide provides the corresponding z-score for the X value. If we draw our normal curve and use the z-score formula, we will find that the z-score for the mean will always produce a z-score value of 0. And the z-score for our endpoints for the normal curve, the value that's 3 standard deviations below the mean, will be a z-score of -3. And the z-score for the value at our upper end of our normal distribution curve, the value that's 3 standard deviations above the mean, will always have a z-score of +3. The standard normal distribution has a mean of 0 and a standard deviation of 1. Recall our steps for computing probabilities for continuous random variables. In step 1, we graph the probability density function. In step 2, we're going to identify the interval of interest on the z-axis. In step 3, we're going to shade in the area under the curve in this interval. And in step 4, we'll determine the area of the shaded region. We will use the cumulative standard normal probability table in order to determine the areas under the standard normal curve. Using the cumulative standard probability table, for any z-score, z sub I, that you look up on the standard normal table, the table will provide the area under the curve to the left of the z-score. Therefore, if you look up the z-score z sub I, the table will give the probability that z is less than or equal to z sub I. Recall, for a normal or for a continuous random variable, the probability of being equal to a value is 0. Therefore, our probability value will not change if it's less than a value or less than or equal to a value. If we want to know the probability that z is less than 1.57, we must look up the z-value 1.57 on the cumulative standard normal probability chart. In order to do this, we go to the chart and we go to the row for 1.5. We go to the column for 0.07. Wherever this row and this column meets, it will provide the area under the curve to the left of that z-score. And so these two values meet at the area 0.9418. Therefore, the probability that z is less than or equal to 1.57 is equal to 0.9418. If we want to know the probability that z is less than 1.90, if we look up the value 1.90 in our cumulative table, the chart will give us this exact probability. In order to look this up, we go to the row that matches the whole number and the number in our tenths place. So we go to the row for 1.9. Then we go to the column that matches whatever number we have in our 100ths position. In this case, there's an implied 0 in this position. Wherever the row and the column meet for our z-score, that is the area under the curve to the left of the z-score. So for this problem, the area to the left of the z-score, 1.9, or the probability that z is less than or equal to 1.9, is the value 0.9713. Now let's go through these practice problems just to make sure that we are comfortable with using the standard normal chart. First, let's compute the probability that z is less than or equal to -1. Remember, if we go to the charts will always give us the probability that z is less than or equal to the z-score that we look up. We go to the chart and go to the row for -1 and the column for 0.00, and we see that this area is 0.1587. Let's determine the probability that z is less than or equal to 1. Since this chart gives us this information directly, if we look up the z-score, 1.0, it will tell us the probability that z is less than or equal to 1. On our chart, we go to the row for 1.00 and the column for 0.00, and we see that that row and column meets up at the value 0.8413. Therefore, the probability that z is less than or equal to 1 equals 0.8413. Let's determine the probability that z is greater than -1. Our cumulative table only gives us the area to the left of a z-score. Therefore, if we go to the table and look up the z-score -1, we would obtain the area less than or equal to, or the area to the left of that z-score. On our table, we go to the row for -1 and the column for 0.00, and we see the area 0.1587. If this area is 0.1587 and we know that the total area under the curve is equal to 1, then the shaded area that we want has to be the difference between 1 and that area 0.1587. Another way of thinking of it is the area that the table gives us is 0.1587 plus the area of the shaded region we could call x. All of that has to equal 1. If we solve that equation for x, we would have to get 1 minus 0.1587, which equals 0.8413. Therefore, the probability that z is greater than or equal to -1 equals 0.8413. For problem 4, let's determine the probability that z is greater than 1. In order to do this, we look up the z-score 1.00 on our cumulative chart, and we obtain the area 0.8413. Remember, this area is the probability that z is less than the value 1, which is this non-shaded area in our graph. Since the total area under our curve is equal to 1, then we know that our shaded area is equal to 1 minus the probability that z is less than 1, or 1 minus 0.8413, which gives us 0.1587. So the probability that z is greater than or equal to 1 is 0.1587. In problem 5, let's determine the probability that z is between 0 and 2. This probability is this shaded area in our curve. If we look up the z-score 2.00 in the chart will give us the probability that z is less than 2. This probability is basically the area to the left of the z-score 2, which from the table is the value 0.9772. Since we know that the area under half of the curve is 0.5, or the area to the left of our mean is 0.5, then we can take the difference between these two values in order to obtain our shaded region. So in this chart, the area from 2 all the way to the left is 0.9772. And the area under the half the chart, which is from the z-score 0 all the way to the left, is 0.5. So the difference between the two is this shaded area, which is 0.4772. Problem 6a, let's determine the probability that z is between -1 and +1. In order to do this, we look up the z-score -1 in the chart, and we find that the area to the left of a z-score of -1 is 0.1587. Then we look up the z-score +1 in the chart, and we find that the area to the left of +1 is 0.8413. So, if the area from 1 all the way over is 0.8413, but the area from this point, which is -1 all the way to the left, is 0.1587, then the difference between these two values will give us this shaded region. And then for this example, this difference is 0.6826. So the probability that z falls between -1 and +1 is 0.6826. Our last problem. Let's compute the probability that z falls between -2.53 and +2. If we look up the z-score -2.53 by going to the row for -2.5 and the column for 0.03, we obtain an area of 0.0057. So the area to the left of the z-score -2.53 is 0.0057. If we look up the z-score +2 in the chart, we find that the area to the left of a positive z-score of 2 is 0.9772. Therefore, the difference between these areas give us the shaded region that we want. For this example, that shaded region is 0.9715. So the probability that z falls between -2.53 and +2 is 0.9715.